Air rips out of your lungs in an instant, not with a Hollywood explosion, and just a quiet, bone-deep terror. Fluids on your tongue, in your eyes, even under your skin begin to boil at body temperature. Consciousness fades in 15 seconds. A minute and a half later, it's over. This isn't merely a hostile environment, it's absolute vacuum where your own biology turns against you. And between that merciless physics and your fragile human body stands only one thing. Not just clothing. A personal spacecraft cut to your exact size. A machine that cheats the vacuum, creating a tiny, portable bubble of Earth. Armor that lets you step into the deadliest place science knows, and come back alive. Today we'll take this engineering masterpiece apart, down to the last molecule. We'll peel back each of its 12 layers. We'll show how a $150 million backpack actually works. And we'll answer one question you may be wondering. Why do astronauts wear a diaper under their suit? From the first stitch to the newest designs built for missions to the Moon and Mars, every secret of the most complex piece of clothing humans have ever made. To survive in that void, a spacesuit has to solve 3 problems, each one sounding impossible. First, it must hold pressure. Without it, your blood would boil. Second, it must provide oxygen where not a single molecule exists. Third, it has to shield you from brutal temperature swings, plus 120 degrees in sunlight and minus 160 in shadow. Spacesuits come in 2 kinds. Lightweight suits for working inside the spacecraft, and the heavy, armored suits built for going outside. We're interested in the latter, the EVA suit. From the outside, it looks monolithic, a single white shell. But beneath that exterior, a system unfolds like a nesting doll. 12 layers, each with its own job, from simple comfort to shielding against micrometeoroids hurtling along at bullet speed. So what is the very first layer, the one closest to the body is made of? Forget nanotechnology and titanium alloys. The very first layer pressed against an astronaut's skin is a diaper. High-tech, engineered for maximum absorbency, but still a diaper. You don't get bathroom breaks during a 6-hour spacewalk. That's the first sobering truth about going to space. Even at the cutting edge of science, astronauts are still human with very earthly needs. Right above that lies something far more interesting. The human body is a furnace. Sealed inside a suit, an astronaut would overheat in a matter of minutes. So under the suit sits a personal water cooling system. A close-fitting garment, threaded with nearly 100 meters of ultra-thin tubing. Cold water circulates continuously through that web, carrying excess heat away from the skin. Essentially, it's an artificial second circulatory system, one that keeps an astronaut alive where the body alone would fail. Only then do the dozen layers we call a spacesuit begin. But it's not just a stack of fabric. It's 3 systems nested like a nesting doll. The first group of layers handles comfort, the cooling and ventilation garment. Next comes the critical part, the airtight shell, an inflatable bladder that creates life-saving pressure around the body. On top of that sits the real armor, 7 alternating layers of mylar, dacron, and other materials that stop micrometeoroids and reflect thermal radiation. Topping it all is an outer layer called orthofabric, a blend of Teflon, Kevlar, and Nomex. Strong, fireproof, tear-resistant, and blindingly white. This isn't a stylistic choice, it's pure survival physics. Space has no atmosphere to scatter sunlight. The sun-facing side can heat to 120 degrees Celsius. In shadow, it plunges to minus 160 degrees Celsius. White reflects the most solar radiation, the only way to keep the suit from turning into an oven. But that many layers are only a flexible shell. They solve pressure and temperature problems, and immediately create a new one. How do you move and work inside a pressurized, cumbersome suit? Where's the skeleton? The rigid frame that lets you bend and reach. And most important, how do you control all those systems when your hands are encased in a dozen layers of protection? Where is the command center of this personal spacecraft? The answer sits right on the chest. Not in soft fabric, but in a rigid fiberglass shell. Engineers call it the hut, the hard upper torso. This isn't just another suit panel, it's the suit's skeleton. The arms, the helmet, the entire life support system attached to this armor-like shell. Everything that turns a pressure suit into a personal spacecraft converges at a single point. It's the foundation that keeps an astronaut alive. And right on that foundation sits the control center. a panel of switches and displays. But look closer and something strange hits you. All the labels on the buttons and toggles read backwards, like a mirror. This isn't a production error, and it isn't an engineer's joke. It's a deliberate, carefully calibrated decision that, at first glance, feels utterly absurd. Why make the simplest thing, the text, unreadable on the most advanced piece of clothing ever built? The solution is both obvious and brilliant. Inside a bulky helmet, an astronaut can't lower their head far enough to see their own chest. The helmet's rim blocks the view. NASA engineers came up with a textbook bit of lateral thinking. They mounted a small mirror on the suit's left wrist. Need to check the readouts? Just raise your wrist to your face. The reflected text on the chest reads perfectly. No electronics, no complex displays. Just optics and ingenuity. Mobility isn't just about where you can look. How do you even move your arms and legs inside an inflated, pressurized suit? Try bending a fire hose while water races through it under pressure. It will fight to straighten with enormous force. A spacesuit faces the same physics. To beat that force, engineers put airtight bearings in every major joint. Shoulders, elbows, wrists, knees. Not simple hinges, but intricate, precision-fitted rings that let your limbs rotate and flex, even as the suit's internal pressure relentlessly tries to freeze the astronaut into an unbending statue. A rigid torso, the command center. Bearings give the crew freedom to move, but that's just the platform. The ship's real heart and lungs bolt on at the rear. A backpack that costs more than several fighter jets. What's inside that $150 million backpack? And how does it handle every astronaut's worst nightmare? A snapped tether and an endless fall into the void. This backpack isn't just a backpack, it's a PLSS, a portable life support system, an autonomous factory strapped to your back. It supplies oxygen, pulls carbon dioxide out of the air, and pumps water through cooling tubes. It costs $150 million. Not because it hides gold or diamonds inside. Its price buys absolute 100% reliability. The price of life. Every tube, every valve, every sensor has a backup. Failure isn't an option. There is no second chance in the vacuum of space. On Earth, the whole system weighs 125 kilograms, about 275 pounds. That's like carrying an adult man on your shoulders all the time. This is not an accessory, this is the suit's heart and lungs. But how does this system solve a problem that seems physically impossible? How do you cool a person in a vacuum, where there's no air to carry heat away? Forget radiators. NASA's answer is clean, icy elegance. Inside the suit's backpack sits a block of ice. The water cooling system channels heat from the astronaut's body into that ice. In a vacuum, the ice doesn't melt. It sublimates, turning straight into vapor and skipping the liquid phase. A special nozzle vents that vapor into space. The heat literally flies away, carried off by water molecules. It's a single-use cooler, brilliant in its simplicity. The refrigerant is nothing more than ordinary frozen water. Still, PORSS doesn't solve every problem. There is one scenario that makes even the most experienced astronaut's blood run cold. One clumsy move, a loosened carabiner, a single second of lost focus, and the safety tether unclips. The station doesn't fly away from you. You do. Slowly, inevitably. In absolute silence, you begin to drift farther and farther from it. Your pulse pounds in your ears. A vast blue and white planet turns below, utterly indifferent. The only island of safety, your one and only home in the entire universe, shrinks with each passing second, collapsing into a bright point you will never reach. Engineers had anticipated this nightmare. Tucked beneath the main backpack sits another, smaller pack. It's safer. A simplified rescue device. A tiny rocket backpack with 24-minute nozzles fed by compressed nitrogen. A joystick rests on the astronaut's hand. One short, precise burst of gas, and the deadly tumble stops. Another, and a slow, life-saving drift back toward the station begins. One last chance. Insurance against the worst nightmare, forged in metal and cold calculation. The spacesuit is a marvel of engineering. Engineers designed and refined it for life in microgravity. It lets astronauts float, repair telescopes, and build space stations. But they built it for the vacuum. A place with no up or down. So what happens when you set this bulky 125-kilogram machine down on the moon? Or Mars, where gravity actually matters? Where you have to walk, crouch, lift rocks, and drill into the soil? How do you turn that awkward, life-saving cocoon into a flexible, rugged tool for conquering another world? An old spacesuit is basically an inflated bubble that fights you at every move. Every step, every bend becomes a struggle against internal pressure that wants to turn flexible joints into rigid tubes. On the moon, under 1/6 of Earth's gravity, the Apollo astronauts didn't so much walk as awkwardly hop, slipping and teetering with every step. Their suits were built for weightlessness, not for working on a solid surface. A clumsy survival shell, fine for staying alive, but no tool for real exploration. The Artemis program tackles that problem in a completely different way. Axiom Space designed the Axiom U not as a beefed-up copy of the old suit. They started from a new philosophy from the ground up. The goal is simple: turn the astronaut from an awkward guest into an effective explorer. Walk, work, dig, build. Not just leave footprints on the moon, actually learn to use it. You notice the difference right away. You don't put this suit on, you step into it. A large hatch opens in the back, the astronaut walks in as if climbing into the cockpit of their own spacecraft, and the hatch seals tight behind them. No more hours of agonizing, suiting up with a team of assistants. The real revolution is in the joints. New bearing assemblies at the shoulders, waist, hips, and ankles give the wearer a freedom of movement that simply didn't exist before. A wide helmet with a panoramic view and built-in HD cameras turns the person inside into a mobile science station. Here's what it looks like in practice. An Apollo astronaut was a fighter, someone who spent most of their strength wrestling with their own suit. They could barely bend to pick up a rock. An Artemis astronaut is a geologist, an engineer, a scientist. They kneel to study the regolith. They turn freely to grab a tool. They walk across the lunar surface with an ease that almost feels Earth-like. This isn't just an upgrade, it's the difference between surviving in a hostile world and conducting thoughtful, full-scale exploration. 15 seconds from blackout. A bare body the vacuum could tear apart. And then, a suit that does more than protect. It grants abilities beyond human limits. The spacesuit stopped being a lifeline. It became an instrument, a symbol of that relentless urge to see what's over the next horizon. This armor isn't meant to hide us from the universe. It's the key to open it.